So tonight we are very fortunate to have Dr. Roger Clark with us. Dr. Roger Clark, I'm going to say some things that aren't in his bio that really impressed me. Dr. Clark worked with Carl Sagan on Cassini. He's worked on Europa Clipper. He's been a major contributor to our astrophotography special interest group. I've had images that I've worked on that he has reviewed, and we've made corrections and learned so very much about astrophotography from him. Also, he has his own website called clarkvision.com. And if you go to it, there's a lot of really good information there about color calibration and imaging in general. So tonight, Dr. Roger Clark earned his Ph.D. in Planetary Science at MIT in 1980. Roger's expertise is in identifying and mapping minerals and other compounds on the Earth, other planets, and their satellites using imaging spectroscopy. He has published over 350 scientific papers, including papers on every planet in the solar system. In 2009, he discovered widespread water on the surface of the moon. He led the USGS, US Geological Survey, environmental assessment of the World Trade Center disaster. He has served on many science teams on NASA missions and is currently on the science team for the Europa Clipper mission that is on its way to Jupiter. And he is on the EMIT science team, an imaging spectrometer on the International Space Station. EMIT is mapping the Earth using Clark software run by NASA on computers at JPL. Dr. Clark is a senior scientist with the Planetary Science Institute. Please welcome Dr. Roger Clark.
So this is a real-time 30 frame per second video that I took up in Alaska over 3 different nights. And it's natural color, high dynamic range. Can we actually turn out the lights? You know, should be enough light coming through the window so it's not too dark. Oh, wow. Yeah, that helps. So this is a 10-minute video. I'm not going to show the whole thing now. Maybe at questions we can do it again, but there's all kinds of rays and curtains and everything going on here. And notice that it's all green. So there's a reason for that, and I'm going to explain that. So I'm going to explain why and how aurora occurs, and what the colors are and why they are some ways and different in other ways. So let's get rid of that. Okay, so I'll show a few images. I have a lot more images on my website that you can see, but this is an image taken in northern Alaska above the Arctic Circle. I'll explain how that's a nice place to go. And notice in this image, there's at the upper end, can you see my cursor online?
Yep.
Yes. So up here, there's red. So red is unusual in the polar regions, but the times that I've been up there have been very low geomagnetic activity, no solar storms at all, yet amazing aurora. Let's see the screen. Here's one night when it was all red and pink and yellow. I mean, just amazing. This is very unusual for polar regions. It's common in equatorial regions with airglow. Let's see. Now, every planet and satellite with an atmosphere has or can have aurora. So here's aurora on these other planets aren't necessarily in the visible part of the spectrum. In this case, this is Saturn, of course, and the green down at the bottom and the South Pole is emission by methane. And methane emits at 3.5 microns. That's like 7 times longer wavelength than green light. So it's in the infrared, you can't see it visually, but instruments, of course, can pick it up. Just every planet has aurora and they're all different. I could spend a whole talk just on that. It's actually not my expertise. I've only technically published one paper on aurora. That was the one with the Saturn aurora. I also worked for Battelle Northwest Labs, who were studying red arc auroras when I was just out of high school and in early college. I worked for them and summers and stuff, and we would take spectrometers out and set them in farmers' fields at different locations to get spectra of aurora. But most of my work is on the surfaces of planets. And so for fun, I do astrophotography and nightscape photography and stuff, and wildlife photography, travel all over to, actually, I've always been interested in astronomy and astrophotography. And in 2000, approximately, I bought a 500 millimeter f4 telephoto lens for the purpose of astrophotography. But people said, hey, you've got to use that for wildlife. And so now I've done a lot of wildlife photography. Okay. So that last one, that's an image here in Colorado. A lot of images from Colorado. This is Airglow. Down low near the horizon is green, and above that is red. It's the same colors, same emission lines as Aurora. It's just a different mechanism. It's just a way they categorize Aurora versus Airglow. Another Airglow picture. This is banded Airglow during the Perseid meteor shower. This was shot in the San Luis Valley in 2015. And of course, it's a composite with all the meteors, but you get the idea of the Airglow, both red and green. Red and green Airglow is very common. There's another, these are called banded Airglows. So when it's lines. Before I understood Airglow, I would see these things when I was out just doing visual astronomy and see these gray waves of what looked like cirrus clouds to me. And then I'd wake up the next morning after sleeping and find it was perfectly clear. And so where'd all the cirrus go? Well, there never was cirrus, it was Airglow. And now that I understand it, and you can see in this image, there's both red and blue, red and green Airglow. That's the banding. The green Airglow is lower down, the red Airglow is higher up. And when you're real dark adapted and the Airglow is reasonably bright, you can tell the colors a little bit. It's a pastel green versus a pastel red. So some of the technical stuff on Airglow and Aurora. So in this plot, from 100 kilometers, that's 62 miles and up, there's a lot of ionization. The chemical bonds that like O2 and N2, they get broken apart, so you get ions. And those ions, when an electron hits them, kicks an electron from the solar wind, kicks an electron in the oxygen atom to a higher energy state, and it sits there for a while and then comes back down and emits a photon. And depending on the altitude, at 90 to 150-ish kilometers, the green transition line occurs. Above that, where the atmosphere is getting thinner and thinner as you go up, above 150 kilometers or so, the oxygen molecules don't run into each other. They're dominant, the blue peak here. So oxygen is the dominant gas or ion that's in the upper atmosphere. And that, because it's a collisionless regime, the green line doesn't happen, but the red line does at 630 nanometers. So up high is red, down low is green. And that's true for both Airglow and the Aurora. So this just explains it in detail. Above about 90-ish kilometers is the thermosphere, and that contains the ionosphere of different regimes. Satellites are flying through the ionosphere, so they constantly have drag and are being pulled back down to Earth due to that drag. The atmospheric density also changes. It changes diurnally with daytime versus nighttime and with geomagnetic activity. So here, and I'll explain K sub P, it's a geomagnetic index of how active the geomagnetic field is. And the higher the K sub P is, the more likely we'll see an aurora at some point. And the greater it is, once it gets up to 7 or so, we tend to see them down south here in Colorado. But occasionally, you can see an aurora, and I'll show you a case where the KP is less than 3. But what this shows is, in the polar regions, as the geomagnetic activity increases, the the atmospheric density increases too, and that biases what you see red versus green airglow, aurora. So in general, at high latitudes, you tend to see green airglow, the oxygen at 90 to 150 kilometers, and at lower latitudes at the equator, the one on the right, the red oxygen line, this was done in Tanzania at 2 degrees south latitude. So the air glow there during the day, solar UV hits an oxygen molecule, kicks an electron to a higher energy state, and it can sit there for days and then eventually come back down. So daytime solar UV creates the excited state in the oxygen atom, and then at night, some of those fall back, and we see that as air glow. So the night sky is not black or blue. It's typically green or red. At mid latitudes, we tend to get both, so we see both of them a lot. A little bit about the colors. So the one thing that I'm intrigued with is natural color photography. Astrophotographers want to get their cameras modified for increased hydrogen alpha. I'm all for natural color because, interestingly enough, it shows more astrophysics. If you bias your camera to one wavelength, like hydrogen alpha, yes, you get a lot of hydrogen alpha, but it swamps all the other things that are going on. So a lot of astrophysics, both in Aurora and in deep space. So Aurora, yellow, green, red, blue, red and blue together make pink or magenta. And when you see combinations, though, sometimes you have green, and then above it, the red oxygen and the green oxygen, and you're looking through, you'll see both colors, so you get different shades of red and yellow and orange. You can also get yellow-orange from sodium. Now, that doesn't seem to be as common. It does seem to be in the ISS astronaut pictures of the edge of the Earth. Below the green airglow at 90 kilometers and up tends to be yellow. And I haven't confirmed this, but I think that might be sodium. Anyway, you can read the other stuff there for deep space. Hydrogen emission is not red, it's pink or magenta due to both blue and red emission lines. So lots of different colors, and in a standard stock digital camera can make a wonderful image that shows the natural colors, and you can tell a lot of astrophysics, from star colors and spectral type to interstellar dust to hydrogen emission and oxygen emission and so on. Here's a case when I was photographing the Milky Way to the south over the San Juan Mountains, and I was at Dallas Divide, which is west of Ridgeway near Ouray in the southeast part of Colorado. And I turned around and I go, hey, it's pink over there. What is that? And below it, it's yellow. And so I turned the camera, and sure enough, I was right. So I could see the colors before I confirmed what they really were. Well, the yellow is the light pollution from Montrose, but above that was pink. And the geomagnetic indices that day was like 2. So apparently what I researched, a coronal hole had opened up and a bunch of electrons spewed out and came, but it didn't affect the geomagnetic index for some reason. I don't know. So any night, regardless of geomagnetic activity, it's possible to see and photograph an aurora. Okay. So this range is the colors that the human eye sees. So blue is down here where nitrogen is. And when stuff is on the outside of this horseshoe, it's very saturated colors. So the green is a yellow green, and if we could see it very intensely, it would appear, as green as it shows on the screen there. And same with the red oxygen. If the red was bright enough and the contrast was high enough, we could see the red. It's not, room light brightness, so we see it as pastel. As things get fainter, we see pastels. Now, there is this idea that colors, both of nebula through a telescope, as well as the Milky Way and things like Aurora, are too faint to see color. That's not true, and I'll show you why in a bit here. Let's see. Get rid of this. Okay. So we're just past solar max. So if you get excited by this talk tonight and want to go out and see Aurora, and I'll describe places to go, got to do it in the next couple of years, maybe 3 years. Then if you don't do it soon, you'll have to wait maybe 6 years for the next solar cycle to come up. So some of the pictures that I've shown here were done in 22 and some this year. And I want to get out the next few years to Northern Alaska or Canada to see more Aurora. But I figure by 27 should be good, 28 maybe, and after 28, I'll drop it. And hopefully 6 years from then, I'll still be mobile enough to try again. Okay, so some of the indices to watch if you want to look for the best chance to see Aurora is the popular one is the K/P index. It's an average of geomagnetic activity from a number of stations around the world. This one's run by NOAA. We hope that NOAA will continue with their budget cuts. I don't know how many things services they'll be able to keep running. So when this plot here, you see the K/P is 5 and below. You're not going to see Aurora in Colorado usually, and except when those unusual conditions like that pink above Montrose that I saw. Once it gets up to 7 and higher, then you have a high chance of seeing the Aurora here in Colorado. If a geomagnetic storm is coming and you're really excited, drive north, or even better, get on a plane and fly north and fly as far north as you can. Germany has this website that, and some of these are already on my website, and I'll give the website at the end. I'm going to add this and other things that are not on the website that are in this talk. I'll be adding them to the website. Don't hold your breath. I'm kind of busy right now with science stuff. But the advantage of the German HP 30 and HP 60 indices, the K/P is done every 3 hours. The HP 30 is every 30 minutes and the HP 60 is every 60 minutes. And my experience with the NOAA KP site is when a big storm is happening, the website crashes and you don't get any response. So go to the German website. They apparently have better computers. Now, there are, besides the HP and the KP indices, there are 3 things to look for. And a high KP doesn't necessarily mean there will be an Aurora. What needs to happen, especially down south in Colorado, what needs to happen is the magnetic field, the Z component, that's the upward component of the magnetic field, needs to be negative. And this plot here, the top, I'm going to go to the next slide, which magnifies it some. So over here, you see this line here is 0, and then it drops below 0. So that's a good sign for the possibility of an Aurora. But then look at the plasma density. The plasma density also dropped. Plasma density is how many electrons and protons are coming in. So with the drop in the plasma density, there's not likely going to be an Aurora. You also want the speed of the incoming stuff to be fast. So you want all of these top 3 to be high. If all those 3 are high and it's clear outside, run out to a dark site and see if you can see an Aurora. There's another predictor website. This is also a NOAA website. If you have a cell phone with a data rate limit, do not use this cell phone. You have to click this. It downloads a lot of data. I don't know, many megabytes, but it gives a predict for several days, and it shows this is the looking down on the solar system here, and then looking vertically up and down above and below the Earth here. So here is, I froze this. Once you click this and download the data, you can move the slider back and forth and see we had a peak in the plasma density. This was on 2016 in November at 1300 universal time. So that's a good time to see a peak that high, a very good chance that we would see an Aurora. would be nice if the plasma velocity was a little higher, but that's still not bad. And it's also interesting to look at this to see how many coronal mass ejections miss the Earth. Because it's neat when they hit the Earth to give us an aurora, but if they're too strong, they can cause a lot of damage. They can destroy satellites. A really big event could burn out power transformers and you would lose power. And a really big event, like happened in the 1800s, if happened today, even a computer that is sitting turned off but plugged in, maybe even not plugged in, would be destroyed. So much energy coming through. That was called the Carrington event, if you want to look it up on Wikipedia. There's another forecast, but it's only a 30-minute. So it tells you really what's going on or what they think is about to go on. Here's two different views. So a lower geomagnetic activity, and then when a good storm is happening. And you see that the lower limit here, this one is above the continental US, and this one is getting closer to the continental US. And notice this is the north celestial pole, but the auroral oval is offset because the magnetic pole is over in this area. So that favors the United States because the magnetic pole is tilted toward us. So that means that the auroral oval is closer to the US, especially the eastern US. Now, interestingly enough, it seems my impression, and I haven't done the statistics, so I don't know if it's true or not, but most of the geomagnetic storms that have hit, and notice, let me go back to this one. Notice how narrow this peak is. The coronal mass ejection goes by the Earth within a few hours on typical storms. This next one, you see this one is narrow, but this one is much wider. That would last for a lot longer, maybe as much as a day. So depending on the width, if the Earth is turned away, then we won't get it at night. It would happen like in Europe at night. And most of the storms in the last couple of years have favored Europe. And, probably just, we complain that it's clear out when it's full moon. But, in reality, it's just biased statistics. Anyway, so there was a nice G2 magnetic storm back in May of 24, and I guess there was one in October. How many saw Aurora last October? There was a good storm, but I was in Florida for the Europa Clipper launch, so I didn't see it. But this one was very nice, and this was only a 2-second exposure, so it was really quite bright. I've been to Iceland, spent 2 weeks in Iceland in 2016, and the aurora tend to be better, more frequent for near the poles at equinoxes, so March and September. And so I was there and I saw aurora on 2 nights, but they were never very spectacular. And if you've been to Iceland, it's cloudy a lot. So go where it's not so cloudy. I grew up in Seattle, and I have many slides on aurora on slide film. And the neatest aurora I've ever seen was one of these times when I was out with Patel with a spectrometer out in a farmer's field, set up the spectrometer, and then just sit and watch the aurora. And I call it, I've never heard it described, but it looked like a campfire, a shimmering lights from horizon to zenith 3 times a second. Most amazing thing I've ever seen. Now, all the curtains dancing and stuff, those are cool too, but they're slow compared to this, what I call the fire aurora. But so if there's ever a big storm and you can get up north, you have a chance of seeing them. If you have a big storm and you go too far north, you might go inside the auroral oval and it would be south of you and you may not see it. So you got to tune your location to the size of the storm. Anyway, I went to this location to do a nightscape of the falls and the Milky Way with Orion rising, and happened to get a G2 geomagnetic storm. So this is Aurora, so a red Aurora. Okay, now to Alaska. So I've been to Alaska, let's see, Werner's with me both times. 2 trips, and one was just this March, and every night we've had wonderful aurora. It's nothing, even the aurora during the twilight when it's not really started up is better than what I've seen in Iceland. And this is at a time when there was no geomagnetic storm activity at all, just very low activity. Now remember, I showed a plot where as the activity increases, the atmospheric density increases. So that biases against red aurora. But here's up above the Arctic Circle, red aurora above the green. So we've been fortunate that I think we've spent 11 or 12 nights above the Arctic Circle now. And we've had red aurora almost every night. So it's been really quite an amazing experience. And one thing about Alaska, central Alaska in March tends to be clear. Okay, so visibility of colors. Here's a test I did with the moon was illuminating my patio, and I put down a Macbeth color chart and then took an exposure and measured the brightness in stellar magnitudes per square arc second. And then I measured the same stellar magnitudes on this one aurora image. And you can see, and let's just pick the green numbers, that's the middle one. So the bright auroral ray here has a magnitude of 17.7. Remember, a bigger number is fainter. So up here where it's fainter, it's magnitude 20. And if we go back, the color tiles were in the 18 range, and the color chart is in the 18 range, and the tiles are similar. So this aurora was brighter than those color tiles. I could tell the color on the color chart and on those rock tiles, the subtle color, just by the moonlight. And this aurora was brighter than that, but I had trouble seeing it. So what I've devised for the next trip, I've taken out that color chart to compare to the Milky Way a number of times. Let's see, let's go back. So I've measured also the brightness of the Milky Way. So the center of the Milky Way, the galactic core, green light is magnitude 20. So that's also fainter than the aurora. The aurora is 7 or 8 times brighter than the core of the Milky Way. And in a dark site, and I know others can see the Milky Way as a yellow-brown, just like in this photo. If we go back, the biggest problem when you have dominant colors is our eye does a sort of automatic white balance. So if everything's green, you have trouble seeing green. So you need a white reference. So I just bought this recently. Let's see if I can turn it on here. Yeah, now I got to put some filters on this to make it darker, but if you set the color temperature, this is something you can put on a camera and to do movies instead of a flash. And this is at 1% of its brightness. So I need to add some neutral density filters to get it, similar to at least magnitude 17 per unit area. So it's comparable to things in the sky. And then I'll have a white reference that I can compare and see that, oh, that aurora is greener than the light or redder than the light or whatever. And same with the Milky Way. So that's a new experiment to do next time with aurora. I've done this with the color chart and the Milky Way, and it works very well. So this should work very well. So this is like $60 versus a great flashlight too. Okay, so this is a pretty highly technical chart, but I'll just to prove to you the science of how the human eye works. And what's going on here is the brightness is here, contrast is vertically, and these lines are the threshold. So for example, if you have a contrast of 0, log 0 is 1. So if you have a contrast of 1, which let's go back to, that's the C here. So that's the red aurora up there. you'd need, this line here is this one, which is 8 arc minutes in size. So if you had a patch of sky at magnitude 20, that's 8 arc minutes in diameter, you should be able to see the color with that contrast. So all of these aurora are in the zone where it's the mesopic, so it's not full enhanced saturated color, so it's more pastels, but you should be able to see them if you have a white reference. So that's the idea of having a white reference. Okay, we're getting close to the end here. Where Werner and I have gone a couple of times now is we fly up into Fairbanks, and out of Fairbanks, you can go to Iceland. I've been to Norway. I've been to Sweden. I've never seen the amount of aurora I've seen in Alaska. You can do aurora tours out of Fairbanks, so it's easy to stay in hotels. You just fly in, you don't even need a car. The tour guides will take you around, and that can work very well. But you need a little bit more activity. But if you go about 300 miles north to the Arctic Circle somewhere, I think about the bottom of Wiseman here. But if you go above the Arctic Circle, anywhere in this region, the auroral oval, when it's low activity, is right overhead. And we've had very few clouds in the 11 or so nights we've been there, and great aurora every night. So the problem is there's no facilities. So fortunately, the road up, I was always concerned about the road. The road is the Dalton Highway where the trucks are constantly going up and down to the North Slope. So it's very, very well maintained. And this mountain was in some of the aurora pictures that I showed. And you stay in rustic cabins, no refrigerator, because outside is the refrigerator. You just use an ice chest. But you do have heat and electricity, so it's really quite nice. But there's only a few of these cabins, so the competition's kind of tough. You have to buy all your food that you're going to do, except for breakfast, depending on the lodge. There's a couple of different lodges. But any lunch and dinner that you have to make it yourself, buy the food. That does save costs. You're not always out at restaurants. So there is a restaurant nearby, 20 miles to the south of Wiseman. So so it's possible, and there are other places to stay, but they're very, very sparse. But if you really want aurora, Fairbanks and north, and I would say that's much better than Iceland or Norway in my experience, which may be limited, but statistics are here. And this one shows, we had some clouds, but we weren't sucked in. So it was great aurora. That's the Dalton Highway there. So it's mostly clear. And so there I'm going to start with a slideshow. Okay, so the colors aren't as vibrant here because these are out of camera JPEGs that I just put together in a time lapse. And no processing. So, and it's done at 5 frames a second, smoothed, so it's not jerky. But it gives you an idea of, so this is like, what? Depending on the exposure times, which range from a second to a few seconds. So it's like 60 times real time, approximately, to first order. And here we have red aurora, a low geomagnetic activity night. It's just amazing. You can see satellites going by. Bonus if you can pick out the constellations. This is a 3-minute video. And then when this is done, I'll put on the real-time video and we can do questions. So my next step, it's a lot of images. These are all single frame images that I'll have to convert the raw data into a high dynamic range color space, and the colors will be much better, but it's a lot of processing. And I haven't had the time to do that. This was done in March, all these images. And this is 2 or 3 days worth of images. Sometimes you'll see the exposure was even 2 or 3 seconds was too long and the JPEG is saturated. This is overhead looking straight up. You can see the Big Dipper in the center there. And these are all with either a 20 or 24 millimeter f1.4 lens. This one actually, except this one, the straight overhead was a 15 millimeter f2.8. It's almost fisheye, so you can see the trees over there on the right. And in the real-time video, I suppressed the sound because you'll hear people yelling in the background with excitement. Also, the temperatures in central northern Alaska, you'd think they'd be frigid. And we have experienced temperatures down to like -13 or so. But on this trip in March, it was surprisingly warm. Most of the time, it was not below -5. So you do need to be prepared. And never had a problem with the cameras. Okay, that's the end. Okay, cancel that one. Okay, so this is real time, 30 frames a second. I tended to only do the 4K video, real-time video, when the aurora was brighter. That means the geomagnetic activity during a local time of, might be 10, 20 minutes, was probably higher. So we tended to not see the red. It was only green. And so you'll see very little red above the green. However, there is something else going on that didn't show in the other images. And you'll see that at the bottom of the green, it turns white, and below the white, you see some purple. What that is, and I'm pretty sure, but I really need to see a spectrum to be sure. And I haven't seen it described quite this way, but it appears to be nitrogen emission. Nitrogen emits in the blue, and it also has some red lines that are weaker, but the red plus blue is purple. So when it's a little bit higher, where you have nitrogen plus oxygen, you have blue plus green plus red, and so that's full spectrum, so it tends to be white. But down below at the bottom where the green is not showing, then we see a tip of just the nitrogen. And you see that in some of these, you'll see the hints of the purple at the bottom. And depending on the sequence, sometimes it's a little more intense. But look at how fast this stuff is moving. In fact, it's moving so fast, 30 frames a second, it's blurred. And it's just stunning to stand there and watch this. Yeah, I've never gotten cold. Too much excitement. Okay, we can do questions while it's playing.
So one of the things that everyone probably wants to know is those charts that you had up there, which ones would you say are the best distillations for saying, oh, we're going to see Aurora in Colorado? So, like there was the NOAA one and the space weather forecast on those two. Those look like good.
There's no certainty, because I've seen Aurora when the geomagnetic indices are low, and I've not seen Aurora when they're high. So it's just a probability. Part of it is if you can get out away from the city lights, and that's quite a ways from Denver, then you have a better chance. You might even just be seeing Airglow. I mean, every night there's Airglow. It's a rare night. I have seen a couple of nights where it is very low airglow, but it's very unusual. Most of the time, it's red or green. And so then the question is it airglow or is it aurora? And sometimes you'll see it's brighter in the north. Sometimes you'll see it's brighter in the south. If it's brighter in the south, it's probably just airglow. If it's brighter in the north, it might be aurora. But then, you know, with airglow, I've never seen rays. So I've seen the banded, more horizontal type stuff, and I've seen pictures. You can find them on NASA Astronomy Picture of the Day, where there's some event from a thunderstorm which has pushed a bunch of air up and fallen down, and that creates ripples in the upper atmosphere up at 300 kilometers high, and you'll see red and green banded airglow in like a ripple in a lake. It's really pretty cool. I've never seen that personally, but I've seen the pictures. So keep an eye out for that. But if there's rays in the north, then it's definitely aurora.
I got an online question from Ron Rannick. He says, can you comment on the atmospheric optical phenomena called STEVE, strong thermal emission velocity enhancement? I've heard it's sometimes mistaken for aurora, but isn't actually aurora.
Right. It's a plasma, a high velocity plasma stream. And it was just discovered in the last 10 years or so. I don't know how well it's understood so far. I mean, it has been determined that it's not an aurora, but what causes it, I haven't seen a good explanation, but I haven't been searching for it either. I may have photographed it on film back in the 70s. But I don't know. I mean, because it was a long exposure, the thing drifted. So it had the mechanisms of such. And we have seen things in in Alaska where it was just a long stream and moving pretty fast. And that could be a component like a STEVE, but I've never confirmed that I've actually positively seen one. So I don't know how common they are. Yeah, it's a good question. Need more data.
You did a lot of the photography with a commercial Canon camera.
Right.
Could you comment a little bit about how you calibrated it? Like as an example, were you shooting at 3800 Kelvin or settings
No,
of 50?
you should, if you want natural colors, whether it's Milky Way, galaxies, nebula, or aurora, it's daylight white balance. And the calibration that is done in the amateur astronomy community is designed in the 1970s for photometry. It's not designed for color. And so when they say a color calibrated in the astrophotography world, it's not actually color calibrated to any standard that we work with to produce reds are reds and blues are blues and so on. To do that, you need to go through a calibrated workflow, which every modern raw converter like Photoshop, raw therapy, Lightroom, they all do all the necessary color calibration steps that are skipped by the astrophotography community. It's been known for more than a decade that the astrophotography community is not doing it, but they still continue to press the 1970 way. So I don't know. It's not that hard. So all of my astrophotos, you go to my website, I have an article called Astrophotography Made Simple. Use Photoshop, stack, stretch, you're done. 3 steps. and it's a better color calibration to natural color than any astrophotography that is done in PixInsight or any of the astro workflows, unless the photographer was aware of all those additional steps. It's called a color correction matrix that needs to be applied. That's specific to every single camera. And most people don't do that or don't even know about it, and it's not taught on websites. So That was, I'm sorry, you got me on my soapbox.
No, I find it interesting because I've been shooting multi-plays for dozens of years. And typically, I see some greens right on the horizon.
Yep, that's Airglow.
That's just the Airglow. But when I get up into the middle, like the center, purples, pinks, and all of that, I'm trying to wonder what's real and what's the calibration issue.
Yeah, there are many issues. So if you're subtracting sky glow to increase contrast, then are you doing it right? And that's one of the toughest problems in astrophotography. We come to the astrophotography special interest group and we can discuss that, but it's very difficult to get it right. And it's often not even obvious what is right. So until we have photometry and spectroscopy of the object, we really don't know what color it should be, and in terms of natural color. So yeah, I mean, you just got to do the best you can. There are hints though. Interstellar dust is reddish brown. The Milky Way is yellow brown. And as you go out from the plane of the galaxy, many photos you see online turn blue. That's not real. That's a mistake in the processing, or an intentional, I want it blue because it looks pretty. There's a lot of people who, it's fine. If you want it blue, that's the photographer's choice, but don't claim it's real.
Thank you.
Joe.
Thank you. Sorry, just one last question. So have you ever shot with a monochrome with filters? Do you always use exclusively RGB?
For my fun stuff, yes, it's always RGB. I did buy recently just to do some experiments and show what really goes on. I bought a dual band filter, but I haven't taken any astrophotos with it. I actually bought it to do some solar imaging. That's another story. But no, I like the natural color. I think it's so unique in the astronomy world that I do that. Professionally, all of my work is narrow, well, not all, but 99% of my work is narrow band imaging. But it's narrow band imaging with imaging spectrometer. So it's not a filter position, it's measure 300 different wavelengths from UV to infrared at one time. So that's what an imaging spectrometer does. So we create images and then you can use the different wavelengths that you measure to determine composition and map composition of all kinds of chemistry and, elements and minerals and so on.
Can you comment further on what is this KP index measuring? Is that part of the magnetic field from the sun, or is it part of the solar system?
No, and I'd have to look it up. I don't remember the details, but it has to do with the Earth's magnetic field and the impact of the solar wind particles hitting the magnetic field. And it's there, and I forget, there's 10, 15, 20 stations around the Earth that are making the measurement, and the KP index is an average of a bunch of them. But you can look it up on the NOAA webpage and get the specifics in case I got something wrong. It's been a while since I looked at that page. Too many indices. There were a lot of questions that I had not resolved to myself, and I worked on those for this talk. So, but one of the things that still confuses me is where the boundaries are. And I came to the realization that you'd measure the boundary in one paper at one level, and then another paper would say something different. Well, the atmosphere is constantly changing, so the boundaries are fuzzy. So there is no, it's 90 to 150 kilometers. It's, if you, especially, it's cool to look at the ISS images. There's an astronomer, well, an amateur astronomer, astronaut, Don Petit, who takes these wonderful images from the space station. He's now come down, but he's got a bunch of images, and he even built a star tracker to compensate for the rotation of the ISS in the two-hour orbit of the ISS. And so he takes star images and shows the edge of the Earth, and the edge of the Earth, then up above it, the green layer, and then the red layer. And they're very, very fuzzy, diffuse layers. So that's not specific boundaries. So a lot of this is fuzzy. Okay.
Any online questions anymore?
I have a question from the web online.
Yeah, we hear you.
Oh, you can. Good. Wow, those are awesome videos, and they're beautiful, and they just are majestic, and holy cow, very well done. The question is, for Aurora on Mars, do the particles actually get down to the funnel down onto and actually hit the surface?
I'm not sure. I can't answer that question. With Mars's atmosphere being thinner, seems like a good possibility. But then Mars is a little further away, so the solar wind isn't as strong. So probably the atmosphere is thin enough for it to happen, but I can't be certain.
If it does happen, then one might expect that perhaps a band around one of the Martian poles has a high particle flux for long periods of time, which might be apparent in the mineralogy or the or the ices at the pole cap. I don't know how that would work. There might be something going on there that could be detected.
Yeah, I can have some colleagues, and I don't recall ever seeing an auroral oval effect on the polar caps, but it's an interesting question.
Those are beautiful videos. I'm impressed.
Thank you. It's so much easier now with the great digital cameras we have and the great lenses, f1.4 lenses that are easy to get. And now with people moving to mirrorless, so all the lenses that I used here are DSLR lenses, even though I'm using them on a mirrorless camera. We just use an adapter. And all the lenses used in this video here I bought used. So because people are moving to mirrorless cameras, the DSLR lenses are going for pretty low cost relative to their original prices. So it's a great time to buy photo equipment.
Any other online questions?
No?